All right, so wanted to run through these problems that I had you start last week, and I want to get through these first 2 pages because that's what you had to do in class last time, and I want you to be able to check your work. So we're going to label some things here. So we're going to label distance, position, displacement, velocity. Now let's just kind of distinguish a couple things here. First, distance and speed. Okay, these two guys, they don't have direction. So they're scalars. The rest of these are vectors. So when we say a Ferrari can go 140 miles an hour, we're talking about a speed. When we say a football field is 100 miles long, that's distance. And I saw most people get this. Hector's house is 7 blocks north of school. That is a position. And I saw people for this when I was walking around the room. They put displacement. Let's be clear on this. Displacement means you moved. So displacement implies movement. There's no movement here. I'm just telling you where you're at. Or where you are, if you want to be grammatically correct. Now, because of the accident, northbound traffic. Oh, we got northbound, so we got a direction, and we got a speed, so that's going to be velocity. And for this last one, it says if you drive 6 miles south on 280 to get to the National Cemetery. We have no idea how long that's going to take. We're simply told you start from your home, you wind up 6 miles south, so you've got a displacement right there. Number 2, we skip that. Give me a sentence which describes, yuck. All right. And then moving on to this next problem here, let's go ahead and take a look. So we have a dog running from 5.3 feet to my left to 1.63 feet to my left in 3 seconds. So let's define some positive and negative here. We're going to say right is positive, and we're going to say left is negative. So let's go ahead and set that up. So what that means is I'm here. So I am right here at the origin. And the dog starts off at negative 5.3. So that's going to be the initial position. And then the dog ends up at a final position at negative 1.6. This is in feet. So now to get delta x, because we need, let's remember, velocity is displacement over time. Average velocity is displacement over time. So we're going to take x final minus x initial, and we're just going to read it off our number line here. So that's going to be negative 1.6 minus negative 5.3, and that gives me positive 3.7 feet. When we say positive 3.7 feet, what we also can read this as is the displacement is 3.7 feet to the right. And then when we want to calculate the velocity, we're just going to say V naught is delta x over time, which is 3.7 divided by 2.3. And when we do that math, we're going to end up getting 1.61 meters per second. Excellent. Now, I didn't have you do part B in class, but I want to review it right now just in case the other teachers decide to put it on the exam. So we have 1.61 meters per second, and we want feet per second. Got to correct that unit. Sorry, it's not meters per second, it's feet per second. And it's feet per second here, so let's go ahead and correct that. So 1.61 feet per second. And now we need to convert that into miles per hour. So we got feet on the top, so we want to get rid of that and put miles on the top. So we're going to put feet on the bottom here, so that's 5,280 feet times 1 mile. So that'll cancel that. That's the bubble method. And then we have seconds at the bottom. We want to get on the top. So remember that it's, and we get hours on the bottom. So we have 3,600 seconds in 1 hour. That's a good thing to memorize. So how did I know this? I memorized it. So you should memorize it. Memorize. Ha ha ha. I look very angry to reinforce that. All right. So we're going to go ahead and then just get this number. So let me just go ahead and crunch those numbers now. So one is giving me, that's weird, I'm getting 1.1 miles per hour. Great. Wonderful. Now, then we have this next one. If the dog continues running at this velocity, where will it be in 1.8 seconds later in feet? So let's be clear. We know the buggy equation says x equals v naught t plus x naught, and we have this dog that's starting from here and it's just running at a constant pace. So we read dog, but really we can think buggy. So x is going to be, and let's be clear on this, the slope, or the v naught is 1.61, so we put that in there. We're going to be 1.8 seconds later. And we have to add our initial position. Now, let's be clear on what we mean. A lot of people are tempted to put negative 5.3 because they're like, oh, we start there. But read very carefully, the word is continues. So what that means is we're in the situation where we started here, but when we start problem 2, we've made it to negative 1.6. And so we need to be very careful in what we calculate. So when we actually calculate this number, we wind up at 1.3 feet to my right because it's positive. That's wonderful. So that's problems 1 and 2. All right, for problems 3, 4, etc., we're going to kind of see more of the same, but let's just sort of get it set up. So here we have west in our direction. So I want to kind of talk a little bit about how directions work when we're doing these things. So if you remember from algebra class, we have the y-axis and the x-axis, and this is positive and this is negative here. So let's be kind of clear. If we can now compare this to a compass, we see that this is north and this is south and this is east and this is west. So you're expected to know basic directions. So what that means is that east would be positive and north would be positive. West would be negative and south would be negative. So that's a good standard to use. If you define your own standard, you're free to do that on the exam, but you're expected to get it right. So you can take a risk and do your own thing, and I'm totally fine with that. Some of you actually will do great at that. But if you're not consistent with your own standard, I'm going to know that because whether you use your standard or my standard, we should get the same answers for things. So here we go. We have a cross-country runner, and so we're going to use school as our reference point. So here's a school. Okay, and we go from 2.5 miles west to 5.2 miles west in 21 minutes. So we want to calculate the average velocity in miles per minute. So let's see how this person runs. So we have, this is x final, and this is x initial. So this is very much like the previous problem. Delta x over t is the velocity, and that's going to be negative 5.2 minus negative 2.5 divided by 21 seconds. So let's go ahead. Negative 2.7 divided by 21. So that's 0.128 miles every minute. Wow. Okay, so that's looking something like a 7-minute mile or an 8-minute mile, something like that. So, okay, I'll buy that. And again, this is going to be in negative miles per minute, which tells us that we're actually running west. Okay, now let's just go ahead and do one more conversion. So let's do part B. I'll do it up here. So let's do miles per hour. So that's going to be 0.128 with a negative sign because we're running rest. Miles per minute times, again, 60 minutes in 1 hour. And so how many miles per hour is that when we do the math? We're going to end up getting 7.68 miles an hour. Wow. By the way, if you wanted to figure out how many minutes there are in this person's miles, what you'd do is you'd actually take the reciprocal of this. So if we take 1 divided by 0.128, what we're basically saying is we're running a 7.81 minute per mile. So that's not exactly the fastest, but not exactly the slowest, I guess. So there you go. Now, I'm going to actually have you take a look at this one on your own, perhaps. But you know what the heck? Let's just do it. So let's convert miles per minute. Let's do part C. So we'll convert miles per minute into meters per second. So we'll do part C right here. So part C. So we're going to take negative 0.128 times, and that's miles per minute. So then what we're going to do is we're going to remember that there is, in 1 minute, there are 60 seconds. because we want to get rid of minutes on the bottom and replace it with seconds. And then we're going to remember that there are, to cancel the miles, 1 mile has 1609 meters. And so we can go through, so then our miles cancel. And so we actually then get our answer, and that's going to be 0.128 with a negative sign times 1609 divided by 605. And let me just make absolutely sure I got that right, because when I look at this math, it looks like I'm getting 0.34 meters per second going west. I've written the west here so I don't need the negative sign, or if you prefer, you can write this velocity as negative 0.34 meters per second. So you're running a little bit over a foot a second, so it's not bad. All right. Now, the above mentioned runner then runs east at the same speed as above. What is the runner's position in miles 34 minutes after she began running east? So let's be clear on this. We have x equals v naught t plus x naught. So we're starting here in problem 4. So we want to know what our position is if we end up running at a velocity of 0.128 miles a minute times 34 minutes plus the initial position that we start at. And so when we actually calculate that, we're going to get 0.128 times 3.4, 0.128 times 34, and we actually end up negative 0.85 miles. So in other words, we wind up 0.85 miles west of our starting point. Okay. And again, we've got to be very careful on what our initial position is, because we're saying then runs. The then means they're starting from here. Okay, going backwards like that. Now, here, the car drives from 52 miles south of San Francisco to 13 miles south of San Francisco in 0.75 hours. And we want to get the average velocities. Here's the city of San Francisco. And we're here. We wind up here. And we're 52 miles south, and we wind up 13 miles south. And again, south is negative, so we have negative 52 to negative 13. And we'll actually go ahead and do that calculation. So to get this is the initial, this is the final. So our displacement is going to be negative 13 minus negative 52. And V naught is going to be our displacement over our time. So 52. So we end up going 39 miles north divided by the time, which is 0.75. And we end up getting that our V naught is 52 miles per hour on this one. Now to get the meters per second, once again, we got 52 miles per hour. I think you should stop the video and try to practice this since you've seen this a couple times. But, you know, pause it and then come back, and then this is what you should do for your calculation. So we have 1 hour contains 3,600 seconds. So, pardon my bad handwriting. Get rid of that. So we have 1 hour contains 3,600 seconds. And then for miles to meters, we got 1609 meters in a mile. So we have 1609 meters in 1 mile. And so when we go ahead and calculate this, we'll end up getting 23.2 meters per second. And again, this is northward. And I would also say northward here for the direction. And that's also why we get a positive for the answer.